Hello, everyone. Welcome to the second session of the day. And actually, we have 3 or 4 time zones. That's why good afternoon, good evening, and good morning. And in this session, we will have 2 short talks and 1 invited talk. And our first speaker is, first of all, I'm Sevilay Sevinçli from İzmir Institute of Technology. Sorry. And our first speaker is Karol Gietka from Okinawa Institute of Science and Technology, and his talk is titled Exponentially Enhanced Quantum Metrology by Quenching Superradiant Light Matter Systems Beyond the Critical Point. Please, Karol, we'll
okay,
listen.
Thank you very much for the introduction. Just let me play. Oh yeah, now it should be good. Yes, so again, hello everybody, and good afternoon. So my name is Karol Gietka, and today I will tell you about my research, exponentially enhanced quantum metrology by quenching superradiant light matter systems. And the motivation behind this research is critical quantum metrology, which attracted a lot of attention in recent years and is associated with driving system exhibiting phase transition close to the critical point of that transition, and is often said to be equivalent to a traditional or standard approach to quantum metrology. In this talk, however, I will try to convince you that this is not the case. I will try to convince you that actually critical metrology is a suboptimal metrological strategy. And once we understand what's the mechanism behind the critical metrology, we will be in the position to easily come up with a method how to improve performance of metrological protocols involving systems exhibiting quantum phase transitions. So this is the outline of my talk. We will start with a very brief introduction to quantum metrology. Then, on the example of a quantum Rabi model, I will explain how critical metrology works. Then I will propose a way of enhancing critical quantum metrology simply by quenching beyond the critical point. Then I will present a potential platform in which the protocol could be implemented. And finally, I will conclude the presentation and give some outlook for future research. Okay, so let's start with quantum metrology. Typically in quantum metrology, what we want to do is to estimate value of an unknown parameter with the highest possible precision. So this is some Hamiltonian. It's very simple right now. Omega is unknown parameter and H1 is some operator. So this omega, for example, can be splitting between the ground state and the excited state that is caused by a magnetic field. And therefore, estimating this omega will give us information about the magnetic field, for example. So now, if we ask the theory of estimation, it tells us that the precision of estimation of an unknown parameter cannot be better than 1 over the square root of the quantum Fisher information, which can be defined using the derivative of the wave function, of the final wave function with respect to this unknown parameter, in this case, omega. And in this sense, quantum Fisher information plays a key role in quantum metrology. And throughout this presentation, we will calculate it for a couple of Hamiltonians. So let's start with this very easy Hamiltonian. So in order to calculate quantum Fisher information, we have to calculate the final state. The final state can be very easily obtained by acting with a time evolution operator generated with this Hamiltonian on the initial state. And then we can plug this wave function into the expression for the quantum Fisher information to get something like this, which is 4 times the t squared, where t is the time during which we imprint the information about the unknown parameter on the initial state, and the variance of this operator H1, which can be understood as a mechanism that imprints the information about the unknown parameter on the initial state psi 0. So now, assuming we have n particles, for example, photons or atoms, we have for classical resources, we cannot overcome the so-called standard quantum limit, which means that quantum efficient information cannot be larger than n, so the number of particles times time to the power of 2. Whereas if we use entangled resources, we are limited then by the Heisenberg limit, which states that quantum efficient information cannot be larger than n to the power of 2 times t to the power of 2. And now, of course, if we have limited resources, I mean limited number of particles and limited time, then we want to be as close as possible to the Heisenberg limit. Of course, this is not that easy because first of all, it requires preparation of entangled state, of a suitable entangled state. And second of all, it requires manipulation of that state, which is not often possible in experiments. So what we can do in order to simplify a metrological protocol is to simply do these things at the same time, right? Now we have a more generic Hamiltonian, which includes two parts. So first part will be used to imprint the information about the unknown parameter, and the second part will be used to create correlations that will elevate sensitivity beyond the standard quantum limit of precision. The question is, what kind of systems should we use? And it turns out that perfect candidates are systems exhibiting quantum phase transitions, because typically near the critical point of the quantum phase transition, the ground state can be extremely non-classical. Very good. So in order to understand how it works, we will now focus on a very simple system, quantum Rabi model, which exhibits a phase transition from a single minimum phase to a double minimum phase, or from a normal phase to a superradiant phase. So quantum Rabi model is a very simple system. It describes interaction between a single mode field, here represented by A dagger and A, with frequency small omega, and single spin, which is here represented by Pauli matrices and energy splitting omega. And this third term is the interaction between a single mode field and the spin. And of course, this third part will be used to create suitable correlations, and we will treat either small omega or capital omega as the unknown parameter. So now if we wanted to calculate the quantum efficient information using this Hamiltonian, it's not that easy, because first of all, we would have to create time evolution operator out of this Hamiltonian, act on the initial state, and take the derivative with respect to some unknown parameter, either small omega or capital omega. However, since in this Hamiltonian, these parts do not commute, a form of such a quantum efficient information will not tell us too much. So in order to simplify a little bit our considerations, we can transform the Hamiltonian a little bit. And if we perform this transformation, which is essentially a rotation of the spin around y-axis and displacement of the field along the real quadrature axis, we can greatly simplify the problem. So here I also defined this critical coupling strength. And if this G is greater than this C, then my system enters this critical or superradiant phase. So if we perform this transformation and restrict to this regime of parameters, the Hamiltonian, the effective Hamiltonian is given by something like this. And now the most important part in this Hamiltonian is...
Karol, do you consider just a single atom or a single two-level particle, or maybe?
Yeah, this is a single two-level atom coupled to a field.
Okay, thank you very much.
Okay, yeah. So now we look at this effective Hamiltonian, and the most important part here is the fact that it only depends on a sigma z, right? It doesn't have dependence on sigma x, which means that if we start dynamics with spin down state, so the eigenstate of sigma z operator, we can simply replace operator with a number, in this case -1, and thus eliminate the spin degree of freedom from the Hamiltonian. So in the end, we have this effective Hamiltonian, which only now depends on the creation and annihilation operators, and we can use it to calculate the quantum Fisher information. So if we do it, the quantum Fisher information will be given by 4 times the variance of this operator. And now in this operator, this capital H lambda, C and D are some operators built out of A dagger and A. They are not that important. The most important part is this two coefficients, this and this, that depend on the energy gap. And now you should see or expect that if we set the energy gap to 0, we will observe a divergence here, like 1/0. And this will, of course, lead to a very large quantum vision information. Unfortunately, it's not that easy, because in order to observe divergence, one would have to also make the nominator different than 0. And this happens only for t of the order of 1 over the square root of the energy gap. And this is this trade-off between the how close to the critical point you are and how long you have to wait is often called the critical slowing down. So the question is, can we avoid somehow this critical slowing down? Can we have large Fisher information, but in a very short time? And in order to answer this question, let us look at this effective Hamiltonian and use the position and momentum operator to rewrite it in this form. So if we look here, this is very simple. This is simply a harmonic oscillator Hamiltonian with tunable frequency, where the frequency depends on G. So now, if we are quenching to the critical point, means that we are quenching from G equal to 0 to GC. Then this term completely vanishes, and we have a Hamiltonian of a free particle, right? Whose eigenstates are maximally squeezed states. And now it's obvious why this critical metrology works, right? You start with a harmonic potential, and you quench it to like an almost flat potential, and then your wave function will experience slow expansion, slow generation of excitation, in this case photons. However, if we now realize that this is the mechanism responsible for creation of excitations and squeezing, we can easily go beyond the critical point and make this an inverted harmonic oscillator, and then use it to stimulate squeezing and make the squeezing much faster than simply expansion of a free particle. Now, if you place a wave function on the top of a hill, it will run down much faster than simply going along flat direction. Okay, so in the regular approach to critical metrology, people are always confined to a normal phase. And in this case, indeed, the best possible strategy is to go as close to the critical point as possible. However, if you realize that this energy gap is only by coincident energy gap, and is actually related to the frequency of that effective harmonic oscillator, then you want to make it negative and exploit the physics of an inverted harmonic oscillator and effectively make this cosine and sine function exponential functions, right? And this exponential dependence on t reflects that you are now forcing excitations to be created. Of course, this effective description of inverted harmonic oscillator doesn't work forever. It's effective description only, and it works until a certain time, until the wave function fills the bottom of the potential. So we can again see it here. In the regular approach to critical quantum metrology, you start with like a nice harmonic oscillator, you quench it to an almost flat harmonic oscillator, and then following a quench, you observe a slow expansion of the wave function. However, if you do it with exploiting the physics of an inverted harmonic oscillator, you can increase the creation of squeezing simply by driving the squeezing, by enhancing squeezing. And of course, this enhanced squeezing will only last until this state will feel the minima of the potential, which are located far away from the tip and are related to this parameter. Okay, so once we understand that, we can now ask ourselves what is the best system to actually implement this protocol. And one of perfect candidates would be atoms in the cavity, interacting with a cavity field, which is known to emulate the decay model. So now, decay model, of course, is a little bit more complex than a quantum Rabi model because it includes n atoms instead of one. But that doesn't change too much. The physics is still the same. We can still exploit the physics of an inverted harmonic oscillator with one significant difference. Now, the coupling parameter will depend on n. And therefore, if we come up with this effective inverted harmonic oscillator and calculate the quantum Fisher information, it will gain an additional exponential dependence on the number of atoms in the cavity. And this can be easily understood because more atoms in the cavity means that there is a greater probability of observing a scattering event for a photon into the cavity field, right? So this is why we have this additional N dependence along with T in the quantum Fisher information. Yeah, and I think this brings me to the conclusions. So critical metrology associated with driving the system close to the critical point is a suboptimal metrological strategy because it requires relatively long times, and it is simply much better to quench beyond the critical point and exploit the stimulated squeezing, which can basically create the same kind of states, but in a much shorter time. Since the states are Gaussian, the standard homodyne detection will lead to the saturation of the classical Fisher information. So this is something I did not tell about, but since the states are Gaussian, there is always a measurement that can extract the maximum amount of information from the system. And as I discussed, it should be possible to implement this protocol in quantum simulators emulating the decay model in the cavity setups. But perhaps the most interesting thing would be to try using this protocol in a spin orbit coupled Bose-Einstein condensate and use its center of mass excitations in analogy to photons to overcome the standard limit of precision, or even some other simulators of quantum Rabi model or decay model that use maybe some exotic excitations, which are much more robust to the coherence or some unwanted effect and elevate the precision to beyond the standard quantum limit. And with this, I would like to thank you for your attention.
Okay, thank you, Karol, for this very clear and timely presentation talk. And now we can have questions. We have time for questions. Let me check the chat box. Okay, I think Ege Özgün has a question, please.
Yes.
Hi, Karol. Thank you for the nice presentation. So I would like to just, can you please comment on this? So do you think it will be possible to engineer a similar mechanism, a similar type of formalism for some many-body systems, such as like a
for Rydberg systems, you said?
No, what I mean is like more like a two-contact magnetic impurity, or just like an Anderson impurity problem, which under Schrieffer-Wolff transformation turns into a Kondo problem. Will it be possible?
So I would say whenever you have a spin, effective spin coupled to a harmonic oscillator, you should be it should be possible to use this mechanism.
Mm-hmm.
So yeah, so if these systems can be described by quantum Rabi model or maybe Jaynes-Cummings model or decay model, it should be possible to exploit this this physics of an inverted oscillator. I believe so.
Okay, maybe then it will be more not non-trivial than that. Okay, thank you very much.
Okay, I think I saw one. Yeah, but please, Barış Çakmak.
Okay, thanks, Karol, for the talk. So it's not an actual question, but I mean, does your Hamiltonian have? I mean, your Hamiltonian looks quite similar to a driven harmonic oscillator with a shortcut to adiabaticity. Do you have any insight, or I mean, does it have any meaning? I mean, this similarity between the Hamiltonian and the
I think there is a loose connection. So yeah, so typically in this shortcuts to adiabaticity, what you do is you control the harmonic oscillator, right? You basically quench your system and then quench back, and this is how you perform shortcut by going through some excited states. So in this case, I would say where is it? It's this Hamiltonian. It is connected to some degree, but we use different aspects of it. Here we want to create a maximum amount of squeezed excitations in the shortest possible time. So there is definitely some relation, but
Okay,
yeah.
I guess there is a paper in Nature Communications, but okay, I need to think about it. There's a Nature Communications paper, I guess, by the University of Milan guys, like Matteo Paris and okay. Anyway, if I remember that, I will let you know. Thanks a lot.
Oh yeah, thank you very much.
Thanks.
Yeah.
Okay. We have one more question, please. Very short one. Onur'dan önce.
Yeah, actually, I was going to ask the exact same question. So, like, I was going to ask about the similarity to counter diabetic drive, and actually, yeah, Barış asked this, so they lower my hand.
Okay,
Yeah,
then.
So,
yeah, thank you. Then Karol once again, and you
thank
can
you very
stop
much.
sharing.